Hello there. So for this exercise we got the set P. We're going to find the set P. That's going to be the set of polynomials of this form. So basically it's a polynomial of degree 1 because it only has s, and the coefficients here a1 and a0 are just elements of the real numbers. So they are both just real numbers. Okay? So this set is going to have it's going to be equipped with the summation and scalar product in the traditional way. So given two polynomials on this set P, we're going to define the first polynomial as a0, a1x and the second polynomial as b0, b1x. So when we pick the summation of these two polynomials, we got a0 plus a1x, b0 plus b1x, and what we're going to do is at the end a group between those coefficients that doesn't have x and those that are multiplied by x. So you can observe that this is a real number, this is also a real number, so we obtain again the same structure of P. So that means that the summation P1 plus P2 is also an element of P. Sorry, here's P. And that's important because this define this is related with the first axiom of vector spaces, because this corresponds to the closure of the summation. And here we got this scalar product, this scalar multiplication of the multiplication of a scalar with a vector. So k p1 in this case is going to be just multiplying in the usual way, k a0, k a1. And here you can observe again that here we have a real number. Here also we got a real number, and that means that this preserves the structure of P. So this also lies on P, and that implies the closure of the scalar product. So here we got the axiom 6 is also satisfied. So the point of this exercise to prove or disprove that this vector P is a vector space, and we have already checked two of its axioms, the first and the sixth, related with the closure of these operations. So let's keep going. The next thing that we need to prove is the commutativity property between the elements of the vector space. So that means that P1 plus P2, this we know that the result is A0 plus B0 plus A1 plus B1x. And what happened here is that these elements here, A0 and B0, A1 and B1, are real numbers. So they commute between each other. That means that this polynomial here is also equal to B0 plus A0 plus B1 plus A1x, and then we can separate the two polynomials that form this polynomial here. So is V0 plus B1x plus A0 plus A1x, and this is just B2 plus B1. So yeah, the next is related with the associativity property, and for that we need to define a third polynomial that the only difference is that the coefficients are going to be determined by the letter z. So let's start with the left hand side of this expression. So P1 plus P2 plus P3 is equivalent to A0 plus A1x, and these two vectors are summed. That means that here we got B0 plus Z0 plus B0 B1 B1 plus C1x. And the next is to sum these two polynomials. Here we got 1, and here is the second polynomial. It is the sum. So when we sum these two polynomials, we obtain a0 plus b0 plus c0 plus a1 plus b1 plus c1 x. Now let's see what happened with the right hand side of this expression. So here we got b1 plus b2 grouped plus b3. So the first polynomial will be a0 plus b0 plus a1 plus b1x and plus here z0 plus z1x. And when we sum these two polynomials, we got a0 plus b0 plus c0 plus a1 plus b1 plus c1x. And you can verify that these two expressions here and here are the same. That means that this axiom is satisfied. Then we need to define the zero vector on this vector space. That means is a vector, in this case we're going to define this way, is just the one that have zero coefficients and that result in just zero and must satisfy this property. If we pick any polynomial that lives on this space P, we obtain again the P. And this part here that I put in the extra effort to write this zero polynomial in this way is to show you that this is actually an element of the polynomials that we have defined, because these two coefficients are reals and have this structure. The only thing is that a1 and a0 are both 0, equals to 0. So it is the zero vector and is on this space. The next, we need to prove that satisfies this property. So given any polynomial, a0 plus a1x plus 0 will return just a0 plus a1x, that is just p. So yeah, it satisfies the fourth axiom. Let's move to the inverse. So the inverse is a polynomial that lives on this space P that satisfies this condition. If we pick any polynomial and we calculate its inverse, we obtain the zero vector or the zero polynomial in this case. So the inverse is going to be defined just by negating the coefficients, or the inverse, the additive inverse on the coefficients. So we can verify that p plus minus p is equals to a0 plus a1x, and here the inverse a0 minus a1x, and this, as you can observe, is equals to 0, just like the zero polynomial. So yes, and I forgot, we need to, well, this inverse satisfies the property that we are claiming here, but the point is that we need to show that this is an element of P, and it is, because each of these coefficients are real numbers, so they are elements of this set P. Now we need to show to prove the axioms of the scalar product, of the scalar multiplication. So in this part, k, it's going to be just a real number, or also called a scalar. So k times multiplying that to the vectors p1 plus p2 will be k a0 plus b0 plus a1 plus b1x, and this is defined in the usual way. That means that k will multiply to each of these elements, and that is equals to k a0 plus k b0 plus k a1 plus k b1x, and this at the end is just we can put together the elements that got an a, gives an in the parentheses, this multiply x. So we can pick those elements that have a as a coefficient. So we got k a0 plus k a1x, and the other elements that got the b coefficients. So k b0 plus k b1x, and at the end this result in k b1 plus k b2. So yes, the axiom is satisfied in this case. Then we got this property. In this case, k and m are both real numbers or scalars. So what happened is that k plus m times the vector p, or polynomial in this case, km act as a one scalar, so this ends as k plus m times a0 plus k plus m a1x, and then all these expressions are real numbers. K, m, and a0, a1 are real numbers, so we can distribute along the parentheses. So we end with k a0 plus m a0 plus k a1 plus k b1x. Sorry, here is not b, here is m. M a1, and then we can group those elements that have k, that are multiplying by k, and we have k times a0 plus a1x, and those that have the m. We can take m as a common factor. We got m a0 plus a1x, and look what we have here is k p1 plus here is just p, kp plus mp. So it is satisfied the 8th axiom. Then we got this the 9th axiom, that is related with the how we can associate vectors that are multiplying by scalar. So k multiplying by the vector mp, this is k times m a0 plus m a1x, and then we multiply again k by this polynomial, and we obtain k m a0 plus k m a1x. So look, both have km, so we can take it out as a common factor. So we got km times a0 plus a1x, and this is just p, so we end with km multiplying p. That is the property that we should prove. So yes. And the last one is just the polynomial times 1, but that is quite trivial. We have 1 here, a0 plus a1x, and then when we multiply this, you obtain just a0 plus a1x, which is again p. So yes. So we have shown that this set p of polynomials of the form a0 plus a1x satisfy the 10 axioms of the vector space, that implies that p is a vector space.